After studying this module, you will learn about Woodward Fieser rules and its applications, and the calculation of wavelength for absorption maximum of different functional groups. Starting off with the introduction of this topic, as we know that the presence of an oxochrome or the extension of a chromophore may cause the change in wavelength and the intensity of the absorption maximum. Now students, Woodward and Fieser were two scientists who formulated a set of empirical rules which could predict the absorption maxima of conjugated systems like dienes, enones, aromatic systems like benzene and its derivatives, and also benzoyl compounds, etc. Let us now explain to you the Woodward Fieser rules. In 1945, Robert Burns Woodward gave certain rules for correlating lambda max with molecular structure. In 1959, Louis Frederick Fieser modified these rules with more experimental data, and the modified rules known as Woodward Fieser rules were formulated. It is used to calculate the position of lambda max for a given structure by relating the type of chromophores present. Now the substituent on the chromophores and the shifts due to the solvent are also considered. Now according to the Woodward Fieser rules, the lambda max of the molecule can be calculated using a general formula, which is like lambda max is equal to the base value for a particular functional group plus the sum of all the substituent contributions plus the other contributions by various other functionalities. Now first of all, we would like to discuss with you students the Woodward Fieser rules for conjugated dienes or polyenes. Now as you know, each type of diene or triene system is having a fixed value for lambda max, which is known as the base value or the parent value. The base value depends on whether the diene is a linear heteroannular or transoid diene or whether it is a cyclic or homoannular diene. Substituents such as alkyl substituents or ring residues or double bond extending conjugations or polar groups such as chlorine, bromine, etc. also contribute to numeral values which add to the base value or the parent value to obtain lambda max for a particular compound. A diene can be a cyclic diene, acyclic diene, homoannular conjugated diene or a heteroannular conjugated diene. Coming on first to the acyclic dienes. An acyclic diene exists mostly in S-trans, that is a transoid conformation, as is shown in the figure in case of butadiene. As acyclic diene can rotate about their single bond to give either a cissoid or a transoid conformation. Therefore, they exist in trans form due to their high stability. Thus, when this diene becomes a part of a ring system, as in 1,3-cyclohexadiene, it is forced into a cissoid conformation because it has attained a ring structure. The wavelength of absorption is shifted to longer wavelengths and the intensity is lowered in comparison with acyclic dienes. The absorption maxima for 1,3-cyclohexadiene is 256 nanometer, whereas for 1,3-butadiene system it is 217 nanometer. Now as you can see, this all is shown in this figure. Coming on to the second kind of dienes, that is the cyclic diene. Cyclic dienes can be classified into three classes depending on whether the double bonds are in same ring or in different rings. Coming on to the first type of cyclic dienes, they are homoannular conjugated dienes. Both conjugated double bonds are in the same ring in case of homoannular conjugated dienes, and thus they are having S-cis or cissoid configuration. The S-cis configuration causes strain which raises the energy of the ground state, while the energy of the excited state is relatively unchanged. Thus, the transition energy is lowered, resulting in absorption at longer wavelengths. Coming on to the second type of cyclic dienes, that is heteroannular dienes. Conjugated double bonds which are present in heteroannular dienes are present in different rings, and thus they have S-trans configuration. The homoannular diene resembles with 1,3-cyclohexadiene, whereas heteroannular diene with butadiene. As you can see these two systems in the figure, first one is a homoannular diene and the second one is a heteroannular diene with their S-trans and S-cis configurations respectively, with their lambda max at 273 and 234 nanometer respectively. Coming on to the third type, which is the endocyclic double bonds. Double bonds present inside the rings can be called as endocyclic double bonds. Now, exocyclic double bonds. Double bonds projecting outside the ring are known as exocyclic double bonds, as can be visualized in these considering specific examples, like in example 2, as you can see, the double bond present within ring B is exocyclic to ring A, whereas endocyclic to ring B. Now, consider and take a look at example 3. Double bond present in ring A is exocyclic to ring B. Similarly, if you see the double bond present in ring B is exocyclic to ring A. Now, as you can just figure out for the rest of the figures, now let me take example number 4, in which both double bonds are present within the ring B, making them endocyclic to ring B, while both the double bonds in exocyclic are exocyclic to ring A. Similarly, in example 5, the double bond present in ring B is exocyclic to ring A and ring C. Similarly, the double bond present in ring A is exocyclic to ring B. Now, last example, the example 6 shows that the double bond is exocyclic to two different rings at a time. In such cases, contribution would be 2 times, not single time, because it is exocyclic to both the rings at the same time or simultaneously. Special note. Now, taking care of the following fact, double bond which is common to both the rings is considered as endocyclic, because at any given point of time double bond will only belong to one ring. Now, stating the empirical rules, that is the Woodward Fieser rules, we will always take the parent value of a butadiene or a cyclic system or a conjugated diene to be 217 nanometer. For a acyclic triene, we will take the value to be 245 nanometer. Base value for homoannular conjugated cissoid diene happens to be 253 nanometer. Base value for heteroannular conjugated transoid diene happens to be 215 nanometer. Now, coming on to the increment values. Increment value for alkyl substituents or a ring residue attached to the parent diene is 5 nanometer. Double bond extended conjugation is given the value of 30 nanometer. The increment value for exocyclic double bonds is 5 nanometer. The polar substituents or the oxochromes and their values. For OCOCH3, the value is +0. For a OR system, the value is +6. For SR system, that is the thio systems, the value is +30. For substituents like chlorine, bromine, the value is +5. And for secondary amines like NR2, the value is +60. Note, all these values are in nanometers. Now, with the help of these rules, students, the UV absorption maximum, that is the lambda max, can be predicted for any alkene compound. Now, some important things which have to be taken care of, I am stating. While calculating lambda max, only those alkyl substituents or ring residues are counted which are directly attached to the carbon atoms, making conjugated system with the compound. Now, if a molecule has both homoannular and a heteroannular diene, which is shown in entry 5, then always use the homoannular conjugated diene as the core chromophore, because it has a higher value of lambda max, that is 253 nanometer. Now, after looking at all the rules and different type of dienes and different values given to various functionalities, let us take now, students, some examples to explain the calculation of a lambda max. Now, first we will look at the entry number 1, which corresponds to a butadiene like system. Now, as you know, for a butadiene system, the base value is 217 nanometers with 2 alkyl groups which give rise to a value of 10 nanometers, 1 exocyclic double bond which give rise to a value of 5 nanometer. Thus, a total of lambda max will become 229 nanometers. Now, coming on to the second entry, as you can see, the second entry corresponds to a homoannular diene. This diene will have 3 ring residues which correspond to a value of 15 nanometer, with the exocyclic double bond having a value of addition 5 nanometer. Thus, calculating the lambda max, it will become 273 nanometers after adding up all the substituents and their contribution to the parent value, which is 253 nanometers. Now, entry number 3. Entry number 3 has a base value of 215 nanometers because entry number 3 is a heteroannular diene, as the double bonds are in 2 different rings. Thus, if you see carefully, it will have 4 ring residues which contribute 20 nanometers. 1 exocyclic double bond contributes 5 nanometer. Thus, adding up all these, we will obtain a lambda max value of 239 nanometers. Now, seeing the entry number 4, it is again a homoannular diene, which is now, but system is different from entry number 2. As you can see, it will have 4 ring residues contributing 20 nanometers, 2 exocyclic double bonds contributing 10 nanometers. Thus, adding up all these, we will get a value of lambda max equal to 283 nanometers. Now, look at entry number 5. Here it is again a little different from all the homoannular dienes that you have studied before in entry number 4 and entry number 2. The base value will remain same, that is 253 nanometers. It will have 6 ring residues. As you can see, there are 2 rings flanking the homoannular system with 2 exocyclic double bonds having a value of 10 nanometers. 1 double bond which is exocyclic to 2 rings will have a value of 10 nanometers. The double bond extending conjugation is the additional factor in this entry. It will add up a value of 30 nanometer. Thus, adding up all these values, we will get a value of 333 nanometers. Now, here is a point to note. Both homoannular and heteroannular systems are present, but we have to choose the system with a longer wavelength, that is the homoannular system. Now, for polyenes with more than 4 conjugated double bonds, there are more empirical rules formulated by Fieser and Kuhn. Fieser and Kuhn rule is used to calculate the lambda max for polyenes. Now, let us consider these rules. Students, Fieser-Kuhn derived the following equation to calculate the wavelength of maximum absorption, lambda max, and also maximum absorptivity. Emax. Now the general formula is lambda max is equal to 114 plus 5x plus y brackets 48.0 minus 1.7y bracket closed minus 16.5 R endo minus 10 R exo. Now in the formula, lambda max is the wavelength of maximum absorption, X is the number of alkyl substituents or ring substituents in the conjugated system, Y corresponds to the number of conjugated double bonds, R endo is the number of rings with endocyclic double bonds in the conjugated system, R exo is the number of rings with exocyclic double bonds in the conjugated system. Emax is equal to brackets 1.74 into 10 to the power 4 bracket closed y. Now here Emax is the maximum absorptivity, y is the number of conjugated double bonds. We can use this Fieser equation to calculate the wavelength of maximum absorbance, that is lambda max, and the maximum absorptivity, that is Emax, for polyenes such as beta carotene, lycopene, etc. Let us specifically, students, take the example of beta carotene. The observed lambda max of beta carotene happens to be 452 nanometer, while the observed Emax is 15.2 into 10 to the power 4. Now you can see here the structure of beta carotene drawn in this figure. Here X is the number of alkyl substituents and that happens to be 10, as you can calculate from the structure. Y is the number of conjugated double bonds, which happens to be 11. R is the number of endocyclic double bonds, which happens to be 2, and the number of exocyclic double bonds, that is R exo, is equal to 0. Thus adding up all the values in the Fieser equation, we will get lambda max is equal to 114 plus 5x plus y brackets 48.0 minus 1.7y bracket closed minus 16.5 R endo minus 10 R exo. After adding up all the values that we have given, get the value is equal to 453.30 nanometers. Calculating Emax of beta carotene, we know that Emax for polyenes according to Fieser equation is 1.74 into 10 to the power 4 within brackets into y. Now calculating for this particular beta carotene structure, y happens to be 11. Thus the value of Emax becomes 19.14 into 10 to the power 4. Now students, taking up another Woodward Fieser rules for another functionality, that is, we will now use Woodward Fieser rules for the calculation of lambda max for alpha beta unsaturated carbonyl compounds. Now students, carbonyl compounds have two principal UV transitions, the allowed pi to pi star transitions and the forbidden N to pi star transitions, as has been discussed in the previous module. In amides, acids, esters or halides, the substituents are NR2, OH, OR or X on carbonyl group, show pronounced hypsochromic shift on the N to pi star transitions. Now the hypsochromic effect is due to the inductive effect of nitrogen, oxygen or halogen atoms. The heteroatom withdraws electrons from carbonyl group and makes carbonyl oxygen lone pairs of electrons more stabilized to its involvement in increasing the C double bond O bond order. As a result, the N to pi star transition of these compounds is shifted to 200 to 215 nanometer range relative to 270 nanometers in aldehydes and ketones. Now moving on, conjugation of the carbonyl group with a double bond shifts the N to pi star transitions as well as the pi to pi star allowed transitions to longer wavelengths. The effect on pi to pi star band is more pronounced than N to pi star. Now, there are Woodward Fieser rules, that is the empirical rules to calculate lambda max for these systems. Woodward formulated rules to predict the position of an absorption maximum in an unknown E known. These rules have been summarized. Now, as was the base value for butadiene, there are base value for acyclic alpha beta unsaturated ketones, and that is 215 nanometers. For 6-membered cyclic alpha beta unsaturated ketones, the value is 215 nanometers. For 5-membered cyclic alpha beta unsaturated ketones, it happens to be 202 nanometers. For simple alpha beta unsaturated aldehydes, it happens to be 210 nanometers, and the value for alpha beta unsaturated carboxylic acids and esters is 195 nanometers. The increment values. Now, the increment value for each double bond extending conjugation is 30 nanometers, and for each exocyclic double bond is 5 nanometers. The increment value for homoannular diene component is 39 nanometers. Is a table which shows you the increment for various substituents. I will tell the substituents, the position and the value hereon. Each alkyl substituents or ring residue in the alpha position will have an increment of 10 nanometers, for beta 12, for gamma 18, for delta 18. For OH group, the increment will be for alpha 35, beta 30, gamma 50 and delta 50 nanometers. For OAC substituents, the increment will be in alpha position 6 nanometer, beta 6 nanometer, gamma 6 nanometer and delta 6 nanometer again. For OME, the value for alpha position will be 35 nanometer, beta will be 30 nanometer, gamma will be 17 nanometer and delta would be 31 nanometer. For chloro substituents in the alpha position, 15 nanometer, beta 12 nanometer, gamma 12 nanometer and delta 12 nanometer again. For bromo substituents in the alpha position, the increment value will be 25 nanometer in the alpha position, 30 for beta, 25 for gamma and 25 for delta position. For the thioester, that is the SR, the value for only mentioned for the beta is plus 85 nanometer, and the secondary amine, the value for beta will be plus 95 nanometer. Now, since the carbonyl compounds are polar in nature, the positions of absorption bands will depend on the solvent used, as has been discussed earlier also, students. Hence, solvent corrections are always required to calculate the value of lambda max. All the above corrections are taken in ethanol as a solvent. Now, for calculating the lambda max in other solvents, one must include the solvent corrections. Now, here is drawn a table from which you can know the solvent corrections. If the sample is prepared in water, we will have a -8 decrease in nanometers. For methanol, you have a 0. For chloroform, you have +1 as an increment in nanometers. For dioxane, the increment value is +5 nanometers, and for ether, the increment value is +7 nanometers, students. And if the sample is prepared in hexane, the increment value will be +11 nanometers. Now, students, you should note that in cross conjugated systems, lambda max is calculated by using highly substituted conjugated systems as a parent system, as we will see in entry number 5. Now, let us see and calculate the lambda max of a few typical examples to elaborate the above rules for alpha beta unsaturated carbonyl compounds. Now, in entry number 1, as you can see in this structure, it is an alpha beta unsaturated carbonyl compound with the base value will be 215 nanometers. 2 alkyl residues will contribute 24 nanometers. Thus, the additive value will become 239 nanometers. In the next one, it is a cyclic system. We still have a base value of 215 nanometers. The alpha substituent, that is on the alpha to the carbonyl group, is having one alkyl group, and thus it will have a contribution of 10 nanometers. In beta position, the alkyl substituents will have a contribution of 12 nanometers. Thus, the addition value will be given as 237 nanometers. Now, coming on to entry number 3, the base value will again be 215 nanometers. I would like to bring to your notice now this double bond next to the carbonyl group is exocyclic to both the rings. Thus, a contribution of 10 nanometers. 1 alpha substituents with a contribution of 10 nanometers and 2 beta alkyl substituents, as you can see in the diagram, will have a contribution of 24 nanometers. Adding them up, you will get a lambda max value of 259 nanometers. Entry number 4, it will have a base value of 215 nanometers plus the different aspect in this structure will be a homoannular diene system giving rise to an increment value of 39 nanometers, 1 gamma substituent with the increment value of 18 nanometers, 2 alkyl substituents with the increment value of 36 nanometers and 1 double bond extended conjugation with the increment value of 30 nanometers. Adding them all up, you will obtain a value of 338 nanometers. Now, the base value in structure number 5 or the entry number 5 will again be 215 nanometers with the 2 beta ring residues contributing 24 nanometers, 1 exocyclic double bond contributing 5 nanometers. The addition value of all these substituents will give you a value of 244 nanometers. Now, coming on to entry number 6. The base value for this will be 202 nanometers because it is a 5-membered alpha beta unsaturated carbonyl system. It has an alpha substituent with the increment value of 10 nanometers, a beta alkyl substituent with the increment value of 12 nanometers, the gamma ring residues contributing 18 nanometers, the delta ring residues contributing again 18 nanometers. As you can see, there is 1 double bond extending conjugation in the system contributing 30 nanometers and 1 exocyclic double bond to the other ring having no double bonds. It will contribute 5 nanometers. Thus, the addition of all these increments to 202 nanometers, it will give you 295 nanometers as the final value. Now, coming on to entry number 7, here you can see the structure is more towards the right hand side because the preferred system is the alpha beta unsaturated system. Now, we will calculate the lambda max keeping in mind this structure on the right hand side of the equilibrium with a base value of 215 nanometer, 1 beta alkyl substituents giving an increment value of 12 nanometers, 1 beta ring residue giving an increment value of 12 nanometers and 1 alpha OH substituent giving a value of 35 nanometers. Adding them all up, you will get a lambda max value of 274 nanometers. Coming on to the final entry, that is entry number 8. Here we have a alpha beta unsaturated acid with a base value of 195 nanometers. It has an alpha substituent arising giving a increment value of 10 nanometers, 2 beta ring residues giving increment value of 24 nanometers and 1 exocyclic double bonds giving a increment value of 5 nanometers. Adding them all up, you will get a lambda max value of 234 nanometers. Now students, we will move on to the third segment of Woodward Fieser rules, that is for the calculation of benzene and its derivatives. Now benzene is a classic example of a molecule with an extended pi electron system. Electronic transitions in benzene could be complex due to closely spaced pi orbitals. Now 3 absorption bands are observed in benzene, due to the obvious pi to pi star transitions. 2 absorption bands at 184, that is having a Emax value of 47,000 and 202 nanometer with the Emax value of 7400 nanometer are called as primary bands, and a band at 255 nanometer having an Emax value of 200 is secondary, which comprises of the fine structure. The most intense peak at 184 nanometer is an allowed transition and is not observed under usual experimental conditions because the absorption at this wavelength lies in the vacuum ultraviolet region of the spectrum. In case of polycyclic aromatic system, this band is often shifted to longer wavelengths. Now, the other 2 low intensity bands at 202 nanometer and 255 nanometer arise from forbidden transitions. Now, the secondary band, as I mentioned, at 255 nanometers is also known as the benzenoid band or the B band and is usually easily identifiable. The B band of benzene or its homologues has a fine structure. When the spectrum is recorded in the vapor phase or in non-polar solvents, the fine structure is caused by the interaction of the electronic energy levels with the vibrational modes. The fine structure is lost if the spectrum is determined in polar solvents or if a single functional group is attached with the benzene ring. In such cases, the reason being the secondary peak appears as a broad peak, thus the fine structure is lost. Substitution on the benzene ring can cause bathochromic shift and hypsochromic shifts. Unlike dienes and unsaturated ketones as discussed above in this module, the effects of various substituents on the benzene ring are not predictable at all. However, qualitative understanding of the effects of substituents on the characteristics of UV visible spectrum can be considered by classifying the substituents into 2 different classes, as we will learn. Now, the first effect is the effect of alkyl substituents. When benzene is substituted with alkyl groups, the absorption bands are shifted slightly to longer wavelength and the fine structure remains intact. The bathochromic shift is attributed to the hyperconjugation effect of alkyl groups. The introduction of a second alkyl group at the para position is most effective in causing bathochromic shift. The para isomer absorbs at the longest wavelength, whereas the ortho isomer has the lowest wavelength. This effect is due to the steric interaction between the ortho substituents, which effectively reduces hyperconjugation. The effect of substituents with non-bonding electrons, which comprises of the second effect. The non-bonding electrons increase the length of the pi system through resonance and cause the shifting of the primary and the secondary absorption bands to longer wavelengths, that is the bathochromic shift. The fine structure of the B band is thus diminished due to broader bands. More is the availability of non-bonding electrons, greater will be the shifting of wavelength towards the longer wavelength, that is the bathochromic shift again. This effect can be easily seen if we compare the absorption spectrum of benzene and phenol. Considering and comparing benzene and phenol, the primary absorption band at 203.5 nanometer shifts to 210.5 nanometers and secondary absorption band at 254 nanometers shifts to 270 nanometers. Further, in negatively charged phenoxide ion, the primary band shifts from 203.5 to 235 nanometers and the secondary band shifts from 254 nanometer to 287 nanometers. Now, we can see that both the bands also show a hypsochromic shift, that is increase in intensity in the phenoxide ion, where there is more non-bonding electrons and they are more easily available for interaction with the aromatic pi system. Similarly, comparing benzene and aniline, the primary band shifts from 203.5 to 230 nanometers and the secondary band shifts from 254 to 280 nanometers. In case of anilinium cation, there are no non-bonding electrons for interaction and hence the absorption properties are quite close to benzene, as the lone pair of electrons is taken up by a proton. Third, we come on to the effect of conjugation, the pi conjugation. If an unsaturated group is directly attached to the benzene ring, then because of pi-pi conjugation, a strong bathochromic shift is observed. The primary band at 203.5 nanometer shifts to longer wavelengths more effectively than the secondary band at 254 nanometer. In some cases, the primary band overtakes the secondary band. For example, benzoic acid shows primary band at 250 nanometer and secondary band at 273 nanometers. But cinnamic acid that has longer chromophore exhibits primary band at 273 nanometer and the secondary band remains merged with it. Similarly, in benzaldehyde, the primary band appears at 242 nanometers and the secondary band at 282 nanometers. But in case of cinnamaldehyde, because of extension of chromophore, the primary band appears at 281 nanometers and remains merged with the secondary band. All this is summarized into this figure as you can see. Now, fourth effect is the effect of electron withdrawing and electron releasing groups on the benzene system. The primary absorption band shifts to longer wavelengths regardless of the electronic effect of the substituents. But as far as secondary absorption band is concerned, electron withdrawing groups such as NH3+, SO2NH2, the cyano group, that is the CN, the carboxylic acid COOH, the COCH3 group, the CHO group, that is the aldehyde group, and the nitro NO2 group, etc. have no effect on the position of secondary absorption unless the electron withdrawing group is also capable of acting as a chromophore. However, electron donating groups such as methyl, chloro, bromo, hydroxy, methoxy and the amino, that the primary amine, etc. increase both the wavelength and intensity of the secondary absorption band. The table given shows the effect of both type of substituents, electron releasing as well as electron withdrawing. Now, as you can see, the effect of electron releasing and electron withdrawing group is clearly seen on the primary and secondary bands and the position is shifted from this table. Now, fifth is the di-substituted benzene derivatives. In case of di-substituted benzene derivatives, it is essential to consider the effect of both the substituents together and then see the effect of band appearing. Then first will be the para-substituted benzenes. In this case, if both the groups are electron donating or electron withdrawing, then they exert similar effects as shown or observed in mono-substituted benzenes. The group with stronger effect determines the extent of shifting of primary absorption bands. Now, if one group is electron donating and the other is electron withdrawing, then the magnitude of shift of the primary band is greater than the sum of the shifts due to individual groups. This is attributed to increased electron shifting from electron donating group to the electron withdrawing group through the pi bond of benzene ring. For example, aniline shows a secondary absorption band at 285 nanometer, which is shifted to 367 nanometer with a significant increase in absorptivity in para-nitroaniline due to the presence of an electron withdrawing para-nitro substituent is shown in the figure with the resonance structures in para-nitroaniline. Let us consider the ortho or meta substituted benzene. If two groups are placed at ortho or meta positions to each other, the magnitude of the observed shift is approximately equal to the sum of the shifts caused by the individual groups. Like Woodward Fieser rules, Scott formulated a set of rules for calculating the absorption maximum of the primary absorption band of aromatic aldehydes, ketones, carboxylic acids and esters. In the absence of steric hindrance to coplanarity, the values calculated are within plus to minus 5 nanometer of the observed value. Now, the base values for aromatic COR systems is 246 nanometer. For the aromatic aldehydes, 250 nanometers, for aromatic acids 230 nanometers and for aromatic esters 230 nanometers again. Now, I would like to instate the increment values for various substituents. The increment values at ortho, meta and para position will be instated according to the alkyl groups. The alkyl group or the ring residue at ortho will have an increment value of 3 nanometers, meta 3, para 10. The OH, the methoxy and the O-alkyl group will have an increment value at the ortho like 7 nanometers, meta 7 and para 25 nanometers. For the oxonium ion at ortho position 11 nanometers, meta 20 nanometers and para 78 nanometers. Now, for chloro at ortho position 0 nanometers, meta 0 and para 10 nanometers. For bromo at ortho position 2 nanometers, meta 2 nanometers, para 15 nanometers. The primary amine group at ortho position will have an increment value of 13 nanometers and meta it will have 13 nanometers and at the para position it will have 58 nanometers increment. The NHCOCH3 group, it will have at the ortho position it will have the increment value of 20 nanometers, meta 20 nanometers and para 45 nanometers. The NHCH3 group, that is secondary amine, methylamine, at the para position it will have an increment value of 73 nanometers. Similarly, the tertiary amine, that is dialkyl, the dimethylamine in particular, at the ortho will have an increment value of 20 nanometers, the meta will have an increment value of 20 nanometers and para it will have an increment value of 85 nanometers. Now, again like the systems before, let us take some typical examples showing the applicability of this Scott rule. Here, as you can see in entry number 1, it will have a base value of 246 nanometers. There are 2 meta substituents, they will contribute 14 nanometers, 1 para substituent will contribute 25 nanometers, thus adding up will have a value of 285 nanometers. In system number 2, here as you can see it is a carbonyl system and ether system as you can see both. So, the base value will be 256 nanometer accordingly. The ring residue at ortho position and increment value to the base value of 3 nanometers. 1 para OCH3 group will have an increment value of 25 nanometers. Thus, adding up the lambda max value will become 274 nanometers. Now, case number 3. The base value here again is 246 nanometers. 2 ortho O-alkyl groups will contribute 14 nanometers, 1 metachloro will contribute 0 nanometers, whereas 1 para O-methyl group, that is the ether group, will contribute 25 nanometers. Thus, the total will become 285 nanometers. Coming on to the heterocyclic compounds. In general, the UV spectra of heteroaromatic compounds are similar to that of their corresponding hydrocarbons. Thus, the absorption of 5-membered heteroaromatics are compared with that of cyclopentadiene, which absorbs near 200 nanometer with the Emax value of 10,000 and near 238 nanometer with the Emax value of 3,400. Pyrrole displays a comparable absorption at 211 nanometer with the Emax value of 15,000 and 240 nanometer, Emax value having 300 value. The absorption at 240 nanometer has a fine structure as observed in the B band of benzene. The presence of an oxochrome or a chromophore substituents on the 5-membered ring causes a bathochromic shift and an increase in the intensity of the bands of the parent molecule. Similarly, the spectrum of 6-membered aromatic heterocycle is comparable with that of benzene, but the B band of pyridine is more intense and has less distinct fine structure because of broader bands. This transition, that is pi to pi star transition resulting in the B band, is allowed in pyridine because of the lower symmetry introduced by the nitrogen atom and hence is more intense than the benzene ring. An increase in the solvent polarity does not affect either the position or intensity of the B band of benzene, but it certainly produces hyperchromic shift on the B band of pyridine and its homologues. Coming on to the polycyclic aromatic compounds. Students, in case of polycyclic aromatic hydrocarbons, due to extended conjugation, both primary and secondary bands are shifted to longer wavelengths. These spectra are usually complicated but are characteristic of the parent compound themselves. The parent band at 184 nanometer in benzene shifts to 220 nanometer in case of naphthalene and 260 nanometer in case of anthracene. Similarly, considering the secondary structure band which appears as broad band around 255 nanometer in benzene is shifted to 270 nanometer and 340 nanometer respectively in case of naphthalene and anthracene molecules. Now students, having finished this module, I would like to now summarize whatever we have learnt till now. We have learnt about the Woodward Fieser rules and its applicability in calculating absorption maxima for several functional groups like conjugated acyclic and cyclic diene systems, alpha beta unsaturated carbonyl compounds. We also learned the Fieser-Kuhn rules for application and calculation of lambda max of polyenes. We have also learned to apply Woodward Fieser rules, also known as the Scott rules, for benzene and its various substituent derivatives, heteroaromatic compounds and the polycyclic aromatic compounds.